For number 2, we have the region bounded by these 4 equations revolved around the line y equals 3. So this is the first one we're doing when it's not around an x-axis or a y-axis. So it's a little bit different, but it's not too bad. Let's go ahead and figure these out. First, to graph these, let's solve them for y. This first one's going to be y equals x squared plus 2. And our line here is going to be y equals 1/2 x plus 1. So I think we've seen something similar to this. We have a parabola that's shifted up 2, and a line, y-intercept of 1, slope of 1/2, so up 1 over 2. And then we have the lines x equals 0, which is just going to be the y-axis, and x equals 1. So we're looking at this region right here. And we're going to revolve this around the line y equals 3. So this is our axis of revolution. Now, we talked about this at the beginning of notes that if we're rotating around the x-axis, it's going to be a dx cut. Rotating around the y-axis, it's going to be a dy cut when we're dealing with discs and washers. Well, which axis does this one look like? Even though we know it's not an x or y-axis, which one does it resemble most? X-axis, right? Because it's horizontal. So it's going to be a dx cut as well. So if our line is horizontal or like the x-axis, it's going to be a dx cut, like one would be around the x-axis. If it's a vertical line that we're rotating around, like the y-axis, it's going to be a dy cut. So for this one, we're going to do a dx cut. So if we look, we don't have to draw the whole thing out here, but if we look at the x revolution, our rectangle's down here. Draw one above the x revolution, same. And then spin it around, we see we've got this flat cylinder with a hole in it that looks like a washer. Again, we kind of know that going into these notes because this is all about washers, but down the road when we have another type of volume that we'll use, it helps to visualize. Alright, so thing to remember with these problems is the little radius is always going to be the distance between the axis of revolution and the closest function. Right, or that part where the rectangle is. So now I should have actually drawn this little radius down here looking at our picture. Right, axis of revolution down to the function. So from the axis of revolution down to the parabola in this case. The big radius is going to be the distance between the axis of revolution and the furthest function. Alright, so in this case, axis of revolution to the end of that rectangle, if it helps you looking at it, but that's going to be to the furthest function. So in this case, axis of revolution to the line. Now, before, it was easy when the axis was just the x-axis or the y-axis. We just used the function by itself because really there was no other reason not to. It was the function y value or the function x value minus 0 because we're going to the axis. But now, when we're finding this distance between the axis of revolution down to the rectangle, we have to subtract. And just like when we're doing area, we either subtract top minus bottom or right minus left. Alright, so we're going to either do top minus bottom, so we're taking the bigger one minus the smaller one, or right minus left. So in this case, we're doing vertical distance. For our little radius, we're going to do top minus bottom. So in this case, the top part to find our little radius is going to be the axis of revolution. Minus the bottom part is going to be the parabola. And you don't necessarily have to write all this stuff every time, but just to kind of so you can see it and look back at it. This is a vertical distance, so it's like a y value. What's the y value of that axis of revolution? 3. Right? What's the y value of the parabola? Well, remember, this is a dx cut, so when I say what's the y value of that parabola, what's the y value in terms of x? Right here is our equation, right? Y is equal to x squared plus 2. So we have 3 minus x squared plus 2 for our little radius. So I would go ahead and simplify that. You can distribute that minus and say our little radius is going to be 3 minus 2, so it's just going to be 1 minus x squared. Then for our big radius, again, it's a vertical distance, so we're doing top minus bottom. So this distance, the top part is going to be the axis again. The bottom part is going to be the line. So our axis of revolution is still y equals 3, minus the y value of the line is just 1/2 x plus 1. So if I distribute that minus, we're going to get 2 minus 1/2 x for our big radius. So now we can set up our definite integral. We have pi times definite integral from the smallest x value, which is what? 0, right? The left side of this is going to be 0. Biggest x value, 1. They give that to us in our equations up here. And then we have big radius squared, so 2 minus 1/2 x squared, minus little radius squared, 1 minus x squared squared.